Okay, welcome to the morning session. It's a pleasure to have Jonathan Sorce here from MIT, and he's going to tell us about relative state counting for semi-classical black holes. John.
Okay, great. Thank you, Onkar. Thank you, everyone. This has been a fun conference so far. I'm looking forward to going through the rest of it. So the subject of today's talk is a paper that I wrote with Chris Akers in April of this year. And the big question, which is an old and important question in quantum gravity, is where does black hole entropy come from? It's an important question. It's one that's been attacked from a lot of angles. And what I'm going to be talking about today is a new angle that's developed over the past few years, which I think is giving us some new and productive insights. So a little bit of history first. Black hole thermodynamics as a field of research starts in the 1970s. And it starts with the observation due to Christodoulou and Hawking, which is that when you are studying classical general relativity, the area of a black hole tends to increase. This seems like sort of an analogy with the entropy of an ordinary matter system in thermodynamics. And indeed, Bekenstein observes in a Gedanken experiment that if you throw matter with some entropy into a black hole, then the area of the black hole tends to increase in a way that compensates for the entropy that you threw in. So this leads people to think that there's some sense in which the area of a black hole plays the role of an entropy, and indeed, there's a deeper analogy having to do with things like first laws of black hole mechanics, where if you perturb a black hole, the amount by which its energy changes is proportional to the amount by which its area changes. So these, are at first, at least, they're formal analogies between the mechanical laws of black holes and the thermodynamic laws of matter systems. But this leads us to ask a question and to make a guess, which is to say, well, maybe the origin of this thermodynamic behavior of black holes is the same as the origin of thermodynamic behavior of ordinary matter systems, which is to say that supposedly, in quantum gravity, black holes, we hope, are going to be complex quantum systems with a number of microstates that is equal to or proportional to, roughly e to the area over 4g Newton. So there's been a lot of very beautiful work verifying this in certain settings in quantum gravity where we have control over the microstates of a black hole system. For example, there's a lot of work, Ashok talked about some of this on Monday, having to do with BPS black holes and supergravity. There's very interesting work having to do with sort of modular invariance and CFT2 and holography and just getting microstate counting from the Cardy formula. There's interesting work having to do with the gravitational path integral that's related to the stuff that Adam was mentioning in the previous talk. And this, the settings in which we can actually sort of compute and prove this are limited, but they're still pretty robust, and they're settings in which we feel like we have a pretty good understanding of what's going on. So we haven't achieved total victory, but it seems pretty reliable to say that in quantum gravity, we can interpret black holes as being sort of emergent ensemble systems with a number of microstates set by the area as the entropy. But there's an interesting gap in this story when you compare it to the story that was told about matter historically, which is that when you're studying thermodynamics of matter, you start just by these empirical thermodynamic rules, and then you develop statistical mechanics, which is a purely classical theory. And then after you develop statistical mechanics, you develop quantum mechanics, and you get a more fine-grained understanding of where these statistics are coming from. The story is different in black hole physics. We started with these empirical thermodynamic observations, and then we went to an understanding in certain settings of the statistical origin of those thermodynamics in quantum gravity. But it seems like there's a link in the chain that hasn't been filled in. What is sort of the analogy of classical statistical mechanics in the language of black holes? In other words, when you're studying matter, you can do statistical mechanics without knowing quantum mechanics. You don't need to know h-bar in order to explain thermodynamics. And you could ask analogously, can we explain black hole thermodynamics without knowing string theory? Is there something that we can do without knowing everything about quantum gravity that lets us understand black hole thermodynamics? And what we're going to be talking about today is that signs point to yes. So the outline of the talk, I'm going to begin, as I often do, with a bit of history about classical and quantum statistical mechanics, because I think it's worth talking about these things in a particular language that's going to help us make the analogy when we study black holes. Then in the middle part of the talk, I'll review this work on the crossed product entropy, which is a very beautiful work that's been developed over the past 3 years by many authors, which is a language for using algebraic tools to study the semi-classical entropies of black holes. And then in the last part of the talk, I'm going to talk about this paper with Chris, where we give this story a state counting interpretation. If you've seen talks on the cross product before, you can fall asleep in these first 2 sections if you like and come back in the 3rd section, but I do think I am going to say things in a new way, so it may be worth paying attention. Yeah.
But the next slide, I was under the impression that statistical mechanics told us that there must be quantum mechanics because phase space comes with its new constant, which is h bar.
I don't disagree with that.
So then what does it mean that statistical mechanics explains without needing to know h bar? Meaning without, it tells us that there is an h bar.
I don't think it does. Statistical mechanics, I mean, okay. I'm going to talk about that in great detail over the next few slides, so maybe we can revisit it if you're not happy with my explanation. Jonathan, did you have a question?
I was going to make a comment, but I can wait until you.
Okay, good. Okay, so let's talk about classical statistical mechanics. So classically, a state is a point in phase space, right? It's a point in phase space, and an ensemble, a statistical system, is a probability distribution on phase space. For example, some thermal state of an ideal gas. Now, indeed, as Bartek was just hinting at, classically, there's no preferred measure on phase space. dxdp is as good as 5 dxdp is as good as any other constant multiplying dxdp. And what this means is that probability distributions on phase space are not canonically normalized. They're only defined up to a multiplicative factor. Indeed, when you develop quantum mechanics, one of the motivations is to fix this by finding some fundamental unit of action that can be used to canonically normalize the phase space measure. But if you don't know quantum mechanics and you only know classical statistical mechanics, you can still talk about these probability distributions on phase space, even though they're not canonically normalized. And you can define the entropy of an ensemble state in the typical way, which is you do some integral of p log p. Now, there's an ambiguity in this expression coming from the ambiguity in the choice of units on phase space. And if you map that ambiguity, you change the measure by multiplying by a constant, and you renormalize the probability distribution with respect to the new measure, then what happens is that the entropy of this ensemble changes by an additive constant. So this is what you can do in classical statistical mechanics without knowing h bar to talk about entropy. And what this means is that because of the ambiguity in units on phase space, total entropy is not defined in classical statistical mechanics, but entropy difference is, because this constant ambiguity is the same for all ensembles at once. Now, indeed, as Bartek says, this does encourage you to develop quantum mechanics because you want to resolve this ambiguity. But even without resolving this ambiguity, you can still use this logic to explain thermodynamics because you can talk about entropy difference and say meaningfully that one ensemble has more entropy than another, therefore is statistically preferred, even if it looks like those entropies are, even if it looks like those entropies are not canonically normalized, maybe they're formally infinite, one of them is still bigger than the other. Yes, Suvrat.
Well, just a comment, you can define entropy differences even if they are much larger than whatever the entropy you're going to find in quantum mechanics. So you can define arbitrarily large entropy differences. And this, maybe I can hold the comment for later, but
okay.
Yeah.
Okay, great. Okay, so indeed, when you decide to develop quantum statistical mechanics, or you develop quantum mechanics, perhaps partially motivated by wanting to resolve this ambiguity, your states are no longer points in phase space. Your pure states are vectors in Hilbert space, and your ensembles or mixed states are density operators. Now, there's two key differences. One is that mixed states are not actually necessarily ensembles. They are actually sort of fundamental states of systems, because a mixed states can arise if a system is entangled with its complement. But the more sort of the really important difference is that the state space of density operators actually does have a canonical normalization, which is provided by the Hilbert space trace. Okay, trace rho equals 1. And what that means is that the von Neumann entropy is unambiguous and absolutely defined as minus trace rho log rho. It has no additive ambiguity. And if you study a microcanonical ensemble, which is a density matrix that's proportional to some projection operator, then the entropy of that density matrix is indeed the logarithm of the dimension of the subspace on which it's supported. And this is the sense in which an entropy is something that counts a number of microstates. And this is a sort of deeper statement than the definition of entropy difference up to, entropy up to an additive constant, because it really gives us the size of the microcanonical Hilbert space on which a state is supported. So this is more or less what we think black hole entropy is getting at. We think that black hole entropy, and we know in some settings that black hole entropy is getting at the logarithm of the dimension of some space on which the black hole is sort of supported or distributed. We're going to talk about the interpretation of this as we go on, But maybe let me sort of emphasize the lessons or the perspective I've been trying to take in what I've been saying so far, which is that when you go from classical to quantum statistical mechanics, two things change. Phase-space distributions become density operators. So these were probability distributions that become operators. And the ambiguous phase-space measure becomes the unambiguous trace. What you're sort of doing is, again, you're taking some functions and making them into operators, and you're taking some measure and you're making it into a trace. And this is actually a language that is very commonly used among mathematicians. Nima even mentioned it during his talk earlier, which is that you can sort of think of the trace as playing it plays the role of a measure on phase space, but it's a measure on an algebra. So it's like some non-commutative measure. And the density operators, well, they're not distributions. Probability distributions commute. They are like non-commuting analogs of probability distributions. And if you look at the mathematical literature, indeed, people call the theory of traces and operators the theory of non-commutative integration. So that's just an interesting comment. That's everything I wanted to say about the history and the analogy that we're going to be pursuing. Now let's talk a little bit about how this language helps us understand black hole entropy at the semi-classical level. So the language that we're going to be using is the language of algebras. It's the same language that Nima was using in his talk earlier. The perspective we're going to be taking is that a general quantum system is going to be described by a collection of operators. These operators are typically arranged into what's called the von Neumann algebra. It's not at all important for this talk that you understand what a von Neumann algebra is. It's a collection of operators that's closed under certain nice operations, and it's typically what shows up in quantum systems. You had a question?
So, just like you said that unambiguous phase-space measures becomes an ambiguous trace, and in the phase-space measure, we expect it to be fixed by the h at the Planck's constant. Do you expect the trace to be fixed in the fully quantum gravity theory to be in somehow?
You're anticipating 2 slides ahead. So good question, but let's get to it then, okay? All right. So for example, these are also examples that Nima used in his talk. If you have some lattice system, then perhaps a subsystem is described by some Hilbert space subfactor, and there's a collection of operators associated to that, which is the bounded operators that act non-trivially on this Hilbert space, but act trivially on the complementary Hilbert space. And even in settings where you don't have Hilbert space factorization, like in quantum field theory, you still have algebras associated with quantum systems. For example, the set of all field operators localized in some causal diamond, some space-time region. So this is very typical. You know, when you're studying a quantum system, if you're studying a subsystem or something like this, you're going to have a collection of operators associated with it that are organized into some mathematical structure. And so we can try to study that structure. And one thing that we do is that we can define density operators. This is the standard definition of density operators in quantum mechanics, which is that if you have some state in Hilbert space and you have some algebra, what you mean by a density operator for the state within that algebra is some positive operator in that algebra satisfying the standard rule for expectation values for everything in that algebra. Trace row A is the vector expectation value of A for every A in the algebra that you're considering. Now, it's an interesting fact that some algebras don't have density operators. And this is a problem. Sorry, there was a question? Oh, okay. Some algebras don't have density operators. And this can happen, for example, if you have an algebra describing a subsystem in which every positive operator has infinite trace. This is typical in quantum field theory due to ultraviolet divergences. And it causes a problem in trying to do the von Neumann entropy version of statistical mechanics in certain quantum systems. But indeed, the non-existence of finite trace operators in QFT seems like a problem for talking about entropy, but as was anticipated by this question a few minutes ago, if you think about classical StatMech, we know that sort of the true measure on phase space is like dx dp over h bar, and that thing looks infinite in the classical limit. So this is something that is sort of well-defined quantumly, but becomes infinite in the classical limit. Nevertheless, you can still do classical StatMech because the measures any constant times dx dp are perfectly good, if ambiguous, and they're not infinite in the classical limit. So this leads us to guess, well, maybe there's some sense in which the QFT trace is like 1 over g Newton, or e to the 1 over g Newton, or some divergent g Newton factor, times the true fundamental trace in quantum gravity. And so this is saying, well, maybe quantum field theory traces look infinite just because we're looking at the g Newton to 0 limit. The quantum gravity trace is fundamentally finite, and perhaps we can still study quantum gravity statistics in the QFT limit if we can get rid of this pesky divergent factor. So that's the goal. That's what we're trying to do. We're sort of working backwards to try to understand what the classical statistical mechanics might look like in this setting. So indeed, in the same way that we could ask about general measures on phase space, symplectic measures, that's just the fact that they're all proportional to dx dp, I don't consider arbitrary measures. In the same way we can ask about general symplectic measures on phase space, we can ask about general traces on von Neumann algebras. This is just some mathematical structure. We can say, well, the Hilbert space trace was divergent for all of the things that we cared about in quantum field theory, but let's look at the other similar mathematical objects that we could define. And if you look at the mathematical literature, they define something called a trace, which is just an abstract quantity that is sort of generalizes the Hilbert space trace. And what it is, it's the map from the algebra to the complex numbers. There's a subtlety here because it can be infinity on some elements, but it's okay to think of it as a map from the algebra to the complex numbers. That is linear and cyclic. So those are the natural properties that a trace should satisfy. And furthermore, you can define some additional well-behaved properties to rule out pathological examples of linear and cyclic maps on an algebra. These have names. They're called faithful, normal, and semi-finite. If you want to understand those terms, they won't be important for this talk, but if you want to understand those terms, you can read this review. But basically, these are like sort of continuity conditions. Faithful, I can't explain quickly, but it is sort of obvious when you write it down that it's the right thing to consider. Normal is like wanting your trace to be continuous, and semi-finite is like wanting your trace not to be infinity on too many elements. You want it to actually sort of at least have essentially a dense set of finite elements. So there are some properties that mathematicians defined. These are like defining a nice set of measures on phase space. This is defining a nice set of traces on an algebra. And anything with these properties we're going to call a renormalized trace, or if you really want to emphasize the connection to the classical statistical mechanical setting, you could call it a non-commutative measure. Now, typically, quantum field algebras admit no renormalized traces. Such algebras are called of type 3. If you've heard these terms floating around, that's all it means. When people say quantum field algebras are type 3, all they mean is that mathematically there is actually a fundamental restriction to defining any one of these renormalized traces. So that's a problem for trying to define entropy consistently in quantum field theory. But in these two very beautiful papers and various generalizations, it was shown that for certain semi-classical algebras in perturbative quantum gravity, so these are not algebras describing quantum field theory systems, they're algebras describing certain systems in semi-classical perturbative quantum gravity. In fact, a renormalized trace does exist, and moreover, it's unique up to scaling, which is sort of like the preferred dx dp that showed up in phase space. An algebra that has this properties is called a type 2 factor. It's okay not to remember these words, but when you see them pop up, what it means is that such a trace exists and it's unique up to scaling. Nima.
So I've been confused about this this analogy for a while now. So the analogy between h bar and g Newton is somewhat subtle because in the limit of h bar going to 0, you get an abelian algebra of functions living on the phase space, right? Whereas in the quantum gravity case, when you take g Newton to 0, you still are describing a non-abelian boundary theory. So, and it's, yeah, one of them is like sort of geometric, well, the mathematical terminology is for geometric quantization. It's just standard quantization that we're familiar with as physicists. The other one has to do with large n matrices. So they're different in nature. And I wonder there's some way of, yeah, I just want to say I've been confused about this analogy.
Yeah, right. So, I mean, obviously it's an analogy, so not all aspects are shared between these two things. The fact that there is an emergent sort of preferred class of measures on phase space is analogous to the fact that there is an emergent preferred class of traces on the semi-classical algebras. But indeed, as you say, other than that, the structures are very different. One is phase space, so it's like totally classical and commutative, and one is an algebra, so it's fundamentally non-commutative. I don't have anything more to say than that, but the problem of the measure is, I think, the same. Yes?
Traces are well defined because of this algebra and so on, while in quantum field theory not, and you are assigning that issue to this divergent factor. But I mean, quantum field theory, we can ask this question about computing entanglement. or things of that kind to in any region. You can ask this question for any region, while in quantum gravity, presumably not, right? You can ask this for regions that are carved out by
Gauge
minimal area
invariant.
surfaces and
Right.
so on. Yeah, in a gauge
Indeed.
invariant way. So if that is the case, then in what sense are we thinking of quantum field theories as limits? Because there now we are also asking
Yeah, good.
more questions.
So really, I probably, okay. This, Oh, Suvrat, so there's a mic behind you. Yeah.
For any region in quantum gravity, because the way these algebras are defined is you have an observer who's used as a reference frame, and then with respect to that, you define something. So these regions are not defined with respect to the boundaries. So my feeling is, first of all, you can do it for any region in quantum gravity using this observer as a reference frame. But that relates to the second question I had, which is...
Well, let me make a comment on this first before we go to the second question, which is, I agree with what you said. I think maybe the important thing to consider is that not every calculation you might want to do in quantum field theory is going to be of this nature. But if you're trying to compute, say, the entropy of some gauge invariantly defined region in the semi-classical limit of quantum gravity, that looks like a QFT calculation that is divergent, but you can renormalize it and make it a quantum gravity calculation that makes sense. But if you don't include any dynamical information and you're just trying to study like the entropy of spin chains in the IR limit, that's going to be a different question. Okay, what was your question?
Question is, I mean, it's related to this. Precisely because these, it's important in these calculations that there's a background entropy. I mean, that's why it works. That's why the type 2 emerges. It tells you there's an undetermined constant in the entropy of precisely the same kind that we had earlier, right? It tells you you only can define entropy differences, which are small compared to the base entropy. So I'm not understanding why you're suggesting that this is somehow fixing the measure, the constant in the entropy. It looks like...
It doesn't, right? In the same sense that, like, okay, I'm not going to be able to just, if I had access to this thing on the right, I would be able to just multiply by G Newton and get something unambiguous that I could study. But I don't have access to this thing on the right. What I'm going to get access to is a family of things that look like 5 times G Newton, 6 times G Newton, 7 times G Newton, and I'm not going to be able to figure out which is the right one. So, but nevertheless, this is exactly like the situation in classical statistical mechanics, right?
Exactly the situation in classical statistics.
Exactly.
Oh, so that's what you want to say. So you don't want to say QFT is like classical statistical mechanics. You want to say this is like classical statistical mechanics.
Yeah,
like
that's
the type 2 stuff.
Indeed.
I see. Okay,
Indeed.
thank you.
Okay. So what I said was typically quantum field theory algebras have none of these nice traces. They're type 3. But these papers showed that for certain semi-classical algebras in perturbative quantum gravity, a trace exists and is unique up to scaling. In a moment, I'm going to tell you about what this class of algebras is, but I want to emphasize the point, which is exactly what I was just saying in response to this question, which is that finding this family is like finding a preferred family of measures on classical phase space. We find a preferred family of non-commutative measures on the semi-classical algebra. Indeed, we can't fix the overall constant, just as we couldn't in classical statistical mechanics, but you do have some information that is very interesting to get at, and that doesn't require microscopic input. So let me tell you about the setting that was studied in these papers. What you start with is the QFT algebra in the exterior of a Schwarzschild black hole. So I'm going to call that a QFT. This is a totally sort of not even semi-classical, it's just a quantum field theory notion. But because I want to study quantum gravity, at least perturbative quantum gravity, I'm going to add a Hilbert space, which is going to describe fluctuations of the mass of the Schwarzschild black hole. Certainly that's a degree of freedom in the quantum gravity theory, and perturbative quantum gravity should include a sector describing fluctuations of the mass. So I'm just going to describe a Hilbert space, which is square integrable wave functions of the changing mass. These are going to be G Newton suppressed mass fluctuations because I'm doing perturbative quantum gravity. When I add this Hilbert space, I get an associated algebra, which I'll call A mass, and it's just the stuff generated by the operator version of this delta M observable. Now, a priori, it looks like I have sort of independent QFT observables and mass observables, but of course those things aren't really independent because in gravity, matter and geometry talk to each other. They talk to each other via Einstein's equations. And what that essentially means, at least at the algebraic level, is that the physical observables are not going to be just things that are in the tensor product of A QFT and A mass, There's specifically going to be things that commute with the difference between the QFT Hamiltonian, I mean the QFT Hamiltonian for the Schwarzschild time, and the mass operator. Because essentially these things should be set equal to each other at the quantum level. Okay? So this is just some algebra that I'm considering, and it's an algebra of operators that shows up when you try to do semi-classical quantum gravity. And what we're going to ask about is its structure. Yes, Nima? Yes. Delta M is going to be... delta M is, I mean, indeed, this is a quantum system, so there are two conjugate observables here. There's like delta M and the derivative of delta M, which is like the boost angle for the black hole. Yeah. Yeah. That's right. That's right. But it's not showing up in the algebra that I'm describing, because I'm just describing the algebra of mass fluctuations, not boost fluctuations, or time shift fluctuations equivalently. Okay, so we can ask about the structure of this algebra. It describes a certain subsector of quantum gravity fluctuations around Schwarzschild, not arbitrary fluctuations, just ones that change the mass. And it has the structure, this formula, if you have ever studied operator algebras, which luckily for us, Witten had, this formula shows up in the mathematical literature on the structure of algebras as something called a crossed product. If you've ever heard those words, it just refers to this structure. And Takayanagi in 1973 studied these. Incidentally, this is the same year that the Four Laws of Black Hole Thermodynamics was published. This structure was studied by Takayanagi, and he showed that when an algebra does have this structure, it has a unique family of renormalized traces, which is exactly what was claimed by these two papers. Right? So we're appealing to the math literature to say that this nice structure that shows up in quantum gravity does have this unique family of renormalized traces. And in fact, Takayangi's paper gives a formula. So you can actually compute with this thing. It gives the formula in terms of QFT quantities. I decided not to write down the formula for this talk, but you can see it in the appendix of this paper I wrote with Christian Jensen and Anthony Speranza. So the upshot is that a rigid mathematical structure gives a preferred family of non-commutative measures for a semi-classical algebra. And you can do some computations with those non-commutative measures. Now, the thing that was studied, or has been studied in great detail so far, is that if you start with sort of Hilbert space states that are factorized between the QFT and a wave function for the mass, then you can use the standard formula for a density matrix to find a corresponding density matrix in A, and you can compute its entropy in a certain semi-classical approximation on the mass wave function. Sharply peaked wave functions are badly behaved, but slowly varying ones can be approximated consistently, and you end up with a formula for the entropy trace rho log rho of such a state, which is a QFT relative entropy between the state you're considering and the Hartle-Hawking state of the black hole, an expectation value of the delta M fluctuation, something that is sort of like a classical entropy for the mass fluctuation, and a constant that can't be fixed, right? The constant is there because of our ambiguity in the scaling of the trace. And one thing that I'm not going to talk about more in this talk, but a reason that people initially got very excited about this is that if you regulate this formula and you try to sort of put in a UV cutoff, what you find is that this is consistent with A over 4G Newton plus S matter plus S mass plus a constant that is an infinite renormalization ambiguity that can't be fixed. But the reason people are excited about this is that this formula is totally UV finite, and there's an ambiguous constant. But if you regulate it, it looks like Bekenstein-Hawking entropy, again up to an ambiguous constant. So as you were emphasizing earlier, and we're maybe about to emphasize again, you don't get Bekenstein-Hawking entropy, but you do get Bekenstein-Hawking entropy differences. And that's compelling. That's right. That's right. That's what the constant does, right? You had a question? Good. So the question is, why did such a simple formula lead to such a dramatic change? Well, okay, I can give you the way I think about it. There's probably a better way that I don't know. But the idea is basically that the QFT operators do not by themselves live in this algebra, because the QFT operators don't commute with the QFT Hamiltonian. right? So the QFT operators, which have all these divergent traces, don't live in this algebra. What does live in this algebra are certain dressed versions of the QFT operators that are sort of dressed by some integrated time flow, essentially. That's sort of the, these are QFT operators that are dressed by some function of HQFT and the delta M. And that dressing, that sort of smearing, you should think of that as regulating out the UV divergences. There's probably a more explicit way of saying this, but I've never seen it done.
Can I ask a question just related to what you said? There's something similar that happens just when you define von Neumann algebras in QFT, which is you have to smear an operator, but
Indeed.
not just in space, a little bit in time.
Indeed.
And then you get something that's well defined.
Indeed.
And so could one say this is like an analog of that? You have to smear things a little bit in time, and that somehow regulates
Yeah, but
divergences?
you're not just smearing things in time within the QFT, you're
I
also
understand.
smearing them in time
so
in
there's
gravity.
an additional degree of freedom that you got, which somehow allowed you to
I
smear.
completely agree. Yeah, I think this is the right analogy.
And Jonathan, can I condition on the mass, or do I have to have?
What do you mean by conditioning on the mass?
Well, if you go to in your next slide where you write these 3 different entropies,
Yeah.
is it? I usually think I walk up to a black hole and it's got a certain mass, and then its entropy is proportional to the area. Here you also have an entropy of the mass.
Oh,
Is
indeed.
the entropy of the area? Is that once I know what the mass is, or is it somehow?
No, I mean, a black hole doesn't really have a fixed mass because a fixed mass black hole is not geometric, because that's like it's like a fixed position eigenstate, right? A black hole is actually a coherent state of the fundamental observables, so it has some distribution of the mass, which maybe you think is a sharply peaked Gaussian or something like that. And if you actually compute entropies in, say, n equals 4 super Yang-Mills theory, you end up with an extra term, which is like the entropy of that wave function. It's related to these log corrections people talk about.
But surely this is very small in comparison to the.
Yeah, it's subleading. It's certainly subleading in G Newton.
So actually,
Could you take the microphone?
Just to make sure you're way of describing what happened when you went to this correspondence version. In simple way, is it that you just consider gauge invariant operators?
Yeah, you consider gauge invariant operators.
Just the individual operators.
Absolutely right. The QFT operators are not present in gravity. It's sort of some gauge invariant combinations of QFT operators and mass dressing and stuff like that. Okay, let's move on to yes. What's the? I can repeat the question if you want to just. Yeah.
So what is this regulator?
What do you mean?
No, you said you regulate it, but what is this regulator? How do you regulate the whole thing? With what?
This is that was sort of an explanation for trying to understand why these observables, the ones that commute with this combination.
No, I was talking about the computation of the.
Oh, good.
How
Okay,
do you
thank you.
regularization.
Indeed. So how do you regulate this to get the right formula? Okay, I will give a very brief answer because there's a lot more I want, well, not a lot more, but there's more I need to get to. What you do is basically you put you have your black hole like this, and you put a hard wall cut off here, which lets you split this state into 2 factorizing things. And then,
is it possible? Is it always possible?
I don't know what you mean by always possible.
Like,
I mean, you do the standard regulator that people do when they put in a UV cutoff to talk about quantum field theory entanglement entropy. It's exactly like that. It's like putting in an epsilon that lets you sort of pretend that the Hilbert space factorizes, even though it really doesn't.
So is that epsilon identified with Planck scale or the string scale?
Neither. I mean, this is a very subtle question that I would say no one really knows the full answer to, but there's a lot of ideas for how these things are supposed to be related. I think I'm gonna move on because this is pretty far off from what I want to talk about. Okay. Yeah, it's from the presence of the Hartle-Hawking state. It comes from, I mean, where it really comes from is, what it comes from is the fact that the observables commute with, it comes from the fact that the thing that shows up in the regulator is delta M or HQFT, and those things are related to the area via the constraints in Einstein's equation. Yeah, indeed. If you look at a higher curvature theory, then the structure of the constraints will change, and you won't be looking. This is the correct constraint for Einstein gravity, and that's what gives you A over 4G. This keeps. Okay. So, good. Okay. So what I've just described. What I've just described is the state of the art as of March of this year. We have a rigid structure giving a preferred family of, I said preferred non-commutative measure, that's wrong, a preferred family of non-commutative measures. And indeed, this gives an associated entropy that agrees with Bekenstein-Hawking up to a constant that can't be fixed. So this is so far really interesting, but it's a mathematical analogy. An open question, or open question as of March, is does the entropy difference induced by these non-commutative measures actually have a state counting interpretation? In other words, can we use this formalism to intuit that certain semi-classical black hole configurations have more or fewer states, even if the number of states looks infinite when you view it from semi-classics? The answer is yes. So what Chris and I studied was the entropy difference in these so-called type 2 algebras in the setting of microcanonical states. So again, microcanonical states are the ones where entropy is expected to count states. And in this algebra that we discussed, a microcanonical mass density matrix is just some operator that's proportional to identity on the QFT tensor a projection onto some mass window. So we're going to study density matrices of this form, and they need to be normalized by some trace. And if you just write what the formal entropy functional is, minus tau projection, blah, 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 appropriately normalized, then you get that the entropy of one of these is exactly what you expect, which is log of the trace of the projection. Now, this is ambiguous up to a scaling in the trace, and we know that we should only consider entropy differences. So the real thing we should study is the difference in entropy between two such microcanonical states, which is a log of the ratio of the traces. So the question we want to ask is, does this have a meaning akin to entropy difference in classical statistical mechanics? The answer is yes. So what we appeal to is a very beautiful theory that was actually sort of developed in the original papers that defined von Neumann algebras by Murray and von Neumann. And it's a general theorem about type 2 factors that the following is true. If you have two projection operators, so P and Q are projections, then their traces are equal if and only if the projections are isomorphic with respect to some isometry, more appropriately a partial isometry, that is in the algebra in question. So the traces are only equal if there is some partial isometry within the algebra that maps the support of P onto the support of Q and vice versa. So indeed, the entropies are equal for these microcanonical states if and only if the microcanonical supports are isomorphic via an isomorphism contained in the algebra. Contained in the algebra is important. We're in infinite dimensions, and we're in a setting where all of these subspaces are infinite dimensional. All of these projections have infinite rank. So indeed, in some formal sense, any two infinite dimension subspaces are unitarily equivalent. The key point is that the entropies of microcanonical black holes are equal if and only if there exists a gauge invariant operator that maps between their supports. So that's the preliminary statement, and that's the preliminary thing that says there's actually some sense in which this entropy difference is telling you that these two infinities in the semi-classical setting are the same, if the entropies are equal. You can generalize this when the traces are unequal. Let's start simple. So let's assume the ratio of the traces of two microcanonical states is a positive integer. And there's a theorem. You can extract this. Yeah. Mm-hmm. The constant in the trace is multiplicative. So the ratio is well defined, right? So it's fine to say that the entropies are equal, or the traces are equal, right? Because the differences are well defined. So I can say the difference is 0. Yeah. Okay. So if the ratio is an integer, then there's a theorem. So again, the traces were equal if and only if one projector could be mapped to the other and vice versa by some partial isometry. If the ratio is an integer, this is equivalent to the projection, one of the projections, being equal to some orthogonal sum of projections that are equivalent to, or isomorphic to, the second one. This expression, if you stare at it, is sort of obviously the right thing. The first projection is equal to a sum over mutually orthogonal projections that are obtained by conjugating the second projection by something in the algebra. There's a productive way to rewrite this, which is by saying that the portion of Hilbert space on which the first projection is supported is isomorphic to the portion of Hilbert space on which the second projection is supported, tensor an n-dimensional, finite dimensional Hilbert space. This isomorphism is constructed only using stuff in the algebra. In fact, you can see that the isomorphism that gets you from right to left just looks like this. Okay, so this is indeed exactly the interpretation that you want. You say that if the exponential of the entropy difference is an integer, then it is exactly the dimension of the additional Hilbert space that you need to map the support of the sort of smaller microcanonical state to the support of the larger microcanonical state. For non-integers, there's like a remainder version of this. You know, a classic sort of thing is that the bigger one can be embedded in some smaller one times an additional factor if and only if the additional factor that you add is big enough. This is exactly what you'd expect in sort of a standard quantum information theory. So the key phrase is that the smaller microcanonical in space can be made to contain the bigger one only if you attach an auxiliary space with dimension at least as big as the entropy difference. This is the key conclusion, and this is, I would say, the fundamental result of the paper. It's telling us that this is exactly the sense in which the entropy difference counts the relative size of the infinities that show up for microcanonical semiclassical black holes. Now, a few comments. Our microcanonical density operators act trivially on the QFT Hilbert space, but the isomorphisms V that map between them actually involve QFT operators. It's not just sort of mass operators that map these things to each other, because those things all commute with each other. You actually need QFT operators to map from one mass space to another mass space. It's related to this idea that sort of pure gravity and pure quantum field theory divergences are problematic, but when you put them together, they make each other work. Another interesting comment is that these isomorphisms are known to exist, but constructing them is hard. The proof that they exist uses the axiom of choice. But the upshot is that while the work clearly shows that algebraic entropy difference encodes the relative size of infinity for distinct microcanonical states, there's still more to do to argue that this explains black hole thermodynamics, because these relative sizes of infinities are very instructive, but we still need an argument that would tell us why an infinity that is bigger in this sense is statistically preferred. So that's one of the future directions that I think we should be looking at. It would be really great to come up with a model of statistical fluctuations in semiclassical gravity that gives rise to black hole thermodynamics from these configurations, that makes the sort of bigger Hilbert space infinities statistically preferred. In other words, what is like the mean free path model? The model of ideal gases that gives rise to statistical mechanics at the classical level. What is the mean free path derivation of black hole thermodynamics in this language? Another interesting thing to look at is that microcanonical states are not the only states for which entropy is meaningful. Entropy is meaningful in compressible states, which are well approximated by microcanonical states. And these things are not yet well studied in the algebraic setting. That's something that we should study more. We have some comments in the paper. Another thing that I think would be really great to look at is that I said things purely in an algebraic language, which is very easy, but it obscures what's actually going on at the level of states. These are all sort of gauge-fixed Hilbert spaces, so the state structure is very complicated. It would be nice to study these things more at the level of states using some BRST formalism. And another thing that I think is really important is I wrote this equation that was like maybe trace QFT goes like 1 over g Newton trace quantum gravity. But at the moment, this is just some formal analogy. It looks like the type 2 trace renormalizes the infinite trace analogously to how multiplying by h bar renormalizes the quantum measure on phase space. But we'd like to see that this is more than an analogy. It would be really nice to see the type 2 trace arise in some semiclassical limit of well-behaved quantum gravity systems. Some interesting comments on that in this paper, but I think a lot more remains to be done, and it's a pretty productive avenue for work in the next year or two. Thank you very much for your attention.
Questions?
A little lost in the last part of your talk. Is there an intuitive physical explanation for what is happening? Presumably it's not just some formal mathematical theorems that are telling us. So what is the physics of this? Just so in a simple...
I'll tell you exactly what the analogy is. Suppose you think about phase space, and suppose you have a box in phase space of volume 1 and a rectangle in phase space of volume 2. Now, the volumes of these things are actually not defined. It's only the ratio of the volumes that are defined because of the h-bar ambiguity in the measure. But the fact that the ratio of the volumes is 2 tells you that you can map 2 copies of this into here using diffs that preserve the symplectic form, right? So you can have like one prime and one double prime. And these can be mapped using diffs that preserve the symplectic form. Completely analogously, you have some subspace of Hilbert space on which one microcanonical state is supported, and some formally bigger subspace of Hilbert space on which I call this rho K2 and I call this rho K1, on which some different microcanonical thing is supported. And the point is that you can take two copies of this and map them here, rho K2 prime, rho K2 double prime, using only equivalences that are permitted by your algebraic structure, in the same way that we could do this using only symplectic form preserving maps. Yes, but what we got what we had in classical statistical mechanics, right? This is not a phase space system. This is very well understood at the level of phase space systems. What I'm showing is that an identical structure arises in this setting, which is not, as Nima emphasized, is not a phase space picture, but it has the same features as the phase space picture in terms of what these relative sizes mean. Nima, could you turn on the microphone?
So if I understood correctly, so you wanted to interpret this shift in the entropy that was arbitrary as an index of inclusion of these type of infinities, right?
Yes. Well,
so the result.
They're type 2 ones, but yes.
Okay, so if they're type 2 ones, that's where my type 2 ones, including type 2 ones, famously has very restricted index. For index less than 4, Von Jones classified them. It takes very discrete values. And for discrete values above 4, it remains an open problem in math. This is a very interesting problem in math. Like mathematicians would love to, if you could make an example in this direction.
Okay, but I mean, this theorem, the only theorem that we used was written in the original On Rings of Operators paper. So this is very well known to mathematicians. Yeah, this theorem. It was proved by Murray and von Neumann in like 1932.
But this is integer n.
For integer n.
You said something about non-integer.
For non-integer n, also from the work of Murray and von Neumann, it's just like it's like a division formula where you have, you know, n copies or n minus 1 copies of the smaller system plus another copy that sort of properly contains the bigger system as opposed to being exactly isomorphic to it.
Let's talk off.
Yeah,
this
okay.
is a very interesting problem.
Yeah.
Thank you.
The key thing is this is an inclusion, not an isomorphism.
One last question.
I mean, here and elsewhere in the paper also you emphasize that this, trace, if the traces are equal, they're related by this isomorphism and so on, and that you emphasize the fact that that should live in the algebra, meaning that it should be gauge invariant. But finally, when you did the counting and demonstrated that when the taus are, one is bigger than the other, it must mean that the dimensions are must be bigger and so on. So where did you use this fact that these guys are gauge invariant?
I used the fact that they're all in the algebra. The theorem is so a map like this will always exist for any microcanonical states if you don't require the map to be constructed from unitaries in the algebra. It's a restriction that if you only let yourself use unitaries in the algebra, then you can only map certain microcanonical states to certain other microcanonical states. It's exactly like the phase space picture. If you let yourself do arbitrary diffs, you can map any phase space volume to any other phase space volume. But if you restrict yourself to doing diffs that preserve the symplectic form, then you can only map things that have the same.
And here, volume. Where is that property going in? That it is part of the algebra?
It's here. I'm not sure what you mean. I mean, it's a theorem that this is only true. Oh, sorry. Good. Oh, no, yeah. It's a theorem that if you have this ratio, then there exists a map like this with these V's in the algebra.
No, but when you say with these V's, I mean, first of all, I mean, if I'm a very naive person, if the dimensions of the two vector spaces is different, of course there cannot be, there has to be some inclusion kind of thing, and not
they're
isomorphism.
I mean, they're all infinite for one thing.
Yeah, But in that case, I mean, this is just true for any sort of VV.
Yeah, yeah. It's the sum. The sum is the thing that you're, right? Each term in this sum is sort of isomorphic to some subspace over here. And it's the sum of all of them, but that becomes the whole subspace. Okay. Yes, but that's the point, right? Is that if you don't put this restriction that they're in the algebra, then you can do this for any two subspaces. But if you restrict yourselves to only letting yourself map with gauge invariant operators, then whether or not you can relate to microcanonical states depends on their entropy difference. So that's the point. The point is it's a restriction that makes it harder to make these isomorphisms and makes it so that the isomorphisms only exist when the entropies allow it.
Okay, let's.
I think
in view of time, maybe
yeah,
we should
yeah,
move on to
we
the
should
next
go
speaker and postpone discussion to lunch. So let's thank John again.